Hello fellow skeptics, I'm Luther Name, and this is the 9th video on the general topic of is there something wrong with modern physics, and if so, what is it and can it be fixed? Now, in the prior videos I've shown how we've not understood the physics associated with the measurements that we've made to try to support the various hypotheses associated with special relativity. These have to do with time dilation, spatial contraction, though we haven't really touched on increase of mass with velocity. But in terms of the other two aspects, length and time, we discussed how the measurements were obviously faulty, and how the understanding of how the Michelson-Morley interferometer worked. We don't know how it works. We thought we did. We think it's very simple, but it's not. The physics is more subtle, and it's been missed. In this one, what we're going to do is delve into the origins of the Lorentz transforms, which are fundamental to special relativity. We're going to delve into where the Doppler came from, and something that's less well understood, less well known. It's less well understood because nobody's paid much attention to it, and that has to do with the aberration. And the aberration itself is very subtle. In a way, it's the most subtle physics associated with the special relativity. And so what we'll do is, I won't delve into the aberration in this video, but I will in later videos talk more in detail on it. The next video, beyond this one, will be talking about the Doppler expression and how we haven't used it correctly, or we haven't used it at all in places that we should have. We've misunderstood it. So with that, let's get to some of the discussion relating to what the Lorentz transforms actually are, where they came from, and then where the Doppler and the aberrations came from. And those will prove to be the only real aspects of special relativity. The kinematic part we'll show later just simply cannot and does not exist. This next series of slides is to show how we currently view the development of things called the Lorentz transforms, and we'll get to those in a few minutes. But what we talk about, at least what Einstein talked about, and the way special relativity is talked about in terms of trying to find or derive the Lorentz transforms, and there was no real way of doing it from first principles. Einstein tried, he failed. His 1905 paper was ridiculed as a result of that. But what you have is a pulse of light that travels in a given reference frame, and it travels in some arbitrary direction in that reference frame. And these are just vectors that represent from the origin out to some time t and some location x, y, z. And these are just a series of representations. This is the vector representation from the origin out to r. This is the square of that. And that comes into play a little bit later. And again, if you just take it linearly, then this looks like Newtonian propagation. However, we can always reorient these things because despite the sphericity of the descriptions and the pulses of light emanating spherically, ultimately we only measure what's along a given ray, which is linear. And so we orient these axes, the stationary and the moving one, in such a way that the light pulse is propagating along the x direction. It just makes it easier with no loss of generality. So what we really need to do, though, is to look at what happens with simultaneity, where we've got a view of the pulse. At the instant the pulse occurs, you have a stationary frame that you reference the pulse as it propagates to, and then you have a moving frame moving at speed v such that it's not stationary, and that as the pulse propagates out, the primed reference frame is moving with it, or in that same direction. It's not moving with the pulse. What we do is we reference the pulse to the coordinates in the prime frame, and we reference the location of the pulse
to the unprimed or stationary frame. This is a depiction of what we're talking about. The reference of that pulse after it's propagating, you have then the original stationary frame, and then you have the frame that's moving with the speed of v, and after some time t, when the pulse is out here, you're relating the relationship of the pulse one frame to the other frame. And since they're both ostensibly looking at the same pulse point at the same time, then what we do is we say, oh, well, they're simultaneous, and so we're going to go ahead and see how they appear or look from one perspective versus the other perspective. And what we do is we find that we have these equations that we showed before. You have one set of equations for the stationary reference frame, and you have another set of equations similar to it for the other moving frame, where x prime is related to x minus vt, the velocity of that frame itself. And you can write various equations. And what happens is that because r equals ct, then r squared equals ct squared, and you can always take and pull them back and make them both equal to 0, as I've shown here. And if they're both equal to 0, then they can be shown to be equal to one another. That's how the Lorentz transforms are found from this equation. The issue is, we know it works. Nobody knows where this comes from. So we'll show you. It's not known where those come from. And Einstein tried to show it, but he couldn't. So let's go back. Let's start with this view again of the two reference frames, one moving, one stationary. But now let's make them simultaneous and say, in the spirit of true simultaneity, what happens when you're both coordinate frames, the moving and the stationary one, are aligned at a given instant at the pulse of light. Well, one frame has a velocity relative to the other, and the other one is stationary. And so you make your references to that point where the two reference frames are simultaneously located. That's the true simultaneity. However, what we've shown so far is not propagation in the normal sense of what we mean by propagation. Propagation of waves satisfies what's called a wave equation. A solution to a wave equation is not those simple expressions like that given here. It's given by an exponential, where this is called the complex phase. And these are just a way they've been represented based on real physical waves like water waves or acoustic waves or what have you. And we define parameters, and we have k, which is called the spatial or propagation vector, and we have the time variation of the frequency. And so we wind up with a propagating wave, and you can reduce this complex form to this form, which is just exactly what we saw before. You should be getting the sense that maybe this is where those other equations came from. But let's just see. Let's go a little further and see if that's where they came from. Oftentimes in these descriptions of the origin of the Lorentz transform, they talk about spherical pulses. This is a two-dimensional pulse. And what happens is that the pulse moves out radially, the wavelengths, and where we make our actual measurements are where we're out here so far that the curvature is pretty flat, and then it's called a plane wave. Then that's what we work with, is plane waves, even though we have descriptions that ostensibly start with either spherical waves and then become plane waves. And we work with the plane waves, not the spherical waves. And so what we have here, we pick a point. Now, the characteristic here is that this complex phase, when x equals ct, this is equal to 0, right? And if that's equal to 0, that's the exponential is 1. And so if we're moving with speed c along this direction, we are ostensibly traveling along the same point on a wave as the wave propagates. You pick a point and wave propagates with some speed, c in this case, and you're staying right there at the same point. So at some location where you've got a point where you can identify what's happening with the wave in its complex phase, you have a moving frame that's incident simultaneously at that same instant of time. and you compare the two. This just reiterates what we're talking about here in the terms of the propagation of the wave itself. So what do we have? If we look at this and go back to the other equations, we have then these series of equations. We have a point that are propagating on the wave itself. What you have is that you can form these equations, again, relative to each of the coordinates, the stationary and the moving equation. And at that particular point where the two coordinate frames, one moving, one stationary, are coincident on the pulse, you can identify these as the elements of the complex phase. And if you've got x equals ct, then you have x squared equals c squared t squared. And what you do is you form both of them equal to 0, and this is where the equation comes from. And they were just selected. There were people over a 20-year period of time during the late 1800s, including Lorentz, who just simply used this. It worked. They didn't know where it came from, but they knew that if they set it up, they could do it. They didn't recognize that it was part of a propagating wave. And it had to be, because you were dealing with propagation of electromagnetic waves. So you needed a wave solution to those equations. But these are Lorentz transforms. These are the equations that satisfy that other equation that I showed on the prior page of the prime versus the unprime values. Both systems of equations equal to 0. So if we go back and take a look at this same setup here, and we look at the complex phase, which is what we're talking about here, at some particular point where we make the two reference frames, the moving and stationary one, coincident at the origin, what we have, if we make that more general, where what we say is, oh, one reference frame is actually moving at an angle relative to another one. This was an important insight that Einstein made. It wasn't something that anybody else had made an observation of, but Einstein did. And he put these things in a three-dimensional form, and this is what those equations go on. The dot is just indicating that you've got a pair of vectors. K vector, a propagation vector, is along the direction of propagation of the pulse. And what you wind up with then are these equations that you must solve. When you solve those equations, you can find the Doppler expression and another expression called the aberration. Both important elements of Einstein's work that prove to be what the real special relativity is. And when we do that, what we find is we can find a Doppler expression. We find that there's a relationship in the primes between the frequency and between the angle. It's called the aberration angle. That's a very difficult concept for most people to understand in its relativistic form. Many people pretend that they understand it, but they don't really. So to start the discussion, and I'm not going to go any further in this particular video, you have the relativistic Doppler equation, which is given by this particular function. In the next video, I'll discuss the aberration. It's more complex, but it's also a richer piece of physics than is normally given credit for. But when the angle phi equals 0, an object is moving in the same direction as the pulse of light. So that's when our primed reference system is moving parallel to the stationary. It's coincident, they're congruent, and the angle phi then is equal to 0, and it's moving in the same direction. If you look at that as a radar beam, and that pulse is a radar pulse, we'd be moving toward a receding aircraft. The aircraft is moving in the same direction as the radar beam and away from the radar. Therefore, the frequency at the aircraft is less, that's the nu prime, it's less than nu, the initial pulse that was that made up that. It should actually be a family of pulses, but let's consider this just to be one of the frequencies that make up the pulse. Nu prime is, and this is a key, nu prime then is also the frequency of the radiation that actually hits the object and bounces back. It isn't it isn't that the object itself is making that change. It's because of the reference frame. At the moving object, it sees or would measure the frequency nu prime. In a radar, if it bounces off the moving object like an aircraft, nu prime then is the scattered frequency back at the radar, and it's from that relationship that we can find what the actual velocity is. Beta, in this case, contains the velocity over the speed of light. We can find beta of thing, and this is a complex. And what happens is when we're in something like a radar, we're looking at the propagation parallel and not at an angle theta. This is equal to 1. And what happens is it becomes a very simple function. It's one that's reduced and used in radar equations. That's all I'm going to talk about in this particular.
So I think we very clearly have shown that the Lorentz transforms are associated with the propagation of electromagnetic radiation, light pulses. It moves with a constant, the pulses move with a constant velocity c. It's a stretch to associate the Lorentz transforms with something like an object moving at some velocity v less than the speed of light. But that's what they did. One of the things that I looked at was, can you actually use the same methodology to find a new type of transform like the Lorentz transforms for an object that is for an object that is moving less than the speed of light? And the answer is you can't. They're not defined. You're left with expressions that have no value. You can't evaluate them. Luther name. That's the end of this video. Please leave some comments and like the video, and let me know if these videos are of any use or any value. Thanks very much. Talk to you in the next video.